Hello everyone, this is Yanamandra from BGC Engineering, here today presenting a paper titled Estimating the Stability of a Vertical Cut Considering Tension Cracks, which is co-authored by Dr. Wong from University of New Brunswick. Here's the outline of this presentation. We'll begin with introduction, followed by background, then methodology, followed by results, and concluded with conclusions and references. Introduction. Unsupported vertical cutting is a primary most activity in most engineering practices. Projects ranging from infrastructure development to mining initiate with this activity. Current regulations for this activity mainly depends on field observations and do not consider factors such as groundwater level, which influences matrix suction distribution, weight of excavation, and an often overlooked factor, tension crack. Tension crack usually shortens the length of slip surface by forming a part of it. It induces an additional pressure head when filled with water and also acts as preferential seepage pathway. Determining the depth of tension crack is quite essential as it has serious implications towards stability of slope and unsupported cuts. Various studies have been performed to determine depth and location of tension crack. However, these studies are applicable only for saturated and homogeneous condition, which often isn't the case on field. In this study, a series of numerical analyses were carried out to analyze the stability of unsupported vertical cut considering the influence of matrix suction and tension crack. Background. Pufall in 1983 came up with an equation to determine active earth pressure considering influence of matrix suction. Vanapali in 1996 extended this equation to show variation of unit weight with suction and a slight modification for internal friction angle. The figure here represents positive and negative earth pressure distribution considering influence of matrix suction. The depth at which net earth pressure is zero will be the depth of tension crack. Methodology. In this study, excavation was simulated on Indian head till. Material properties are summarized in the table shown here. The curve on left represents the soil water characteristic curve for this material, and curve on right represents the hydraulic conductivity function for the same material. Geotechnical modeling software ICGE2020 R2 was used with tools such as Sigma W and Slope W. For Sigma W, which was used as parent analysis, in situ analysis was used to develop initial conditions, and excavation was simulated using coupled stress analysis. Material model for this tool was elastic plastic, and to perform the slope stability analysis, Slope W tool was used. Analysis type of Sigma W stress and material model of Moore column. To simulate the excavation, fine meshes of size 0.1 meter were generated at the vicinity of excavation using quadrilateral and triangular mesh pattern. Stress-strain boundary condition represented by hollow triangles was used to restrain horizontal and vertical movements at defined locations. Hydraulic boundary condition represented by blue circles was used to maintain a constant total head depending on the level of groundwater table. Excavation was performed in a sequential manner by deactivating a region and performing consequent slope stability analysis until a desired depth was achieved. Entry-exit slip surface was used and exit point was assigned at the toe of the vertical cut. Excavation was simulated at two different heights. Safe height defined as excavation performed until a factor of safety of 1.2 was achieved, and critical height defined as excavation performed until a factor of safety 1.0 was achieved. Simulating tension crack. In this study, tension crack was simulated as a void. Slip surface was assumed to initiate at the bottom of tension crack and exit point was located at the toe of unsupported vertical cut. Depth of tension crack was defined using the formula presented as depth ratio, and same goes with the distance. Initial condition of unsupported vertical cut with factor of safety 1.2 was taken under equilibrium condition, and depths and distance of tension crack were varied until factor of safety fell below 1.0. Results for both analytical and proposed tension crack model were plotted. Figure on left represents the analytical model where depth of tension crack is 1.34 meters and critical height is 2.5 meters. This gives us a depth ratio of 0.64. Based on the obtained results from proposed tension crack model, a chart was plotted as shown on right. Here, the blue area is the zone of depth ratio prior to failure, while red area is the zone of distance ratio prior to failure. These results were then compared with the ones provided in the literature, and it was found that cut might actually fail prior to reaching the depths proposed by Vallejo or depth which was obtained through the analytical model. It can also be seen that the distance ratio, when compared with OSHA 2019, the cut might actually fail prior to reaching the distance ratio proposed by OSHA 2019, which is 0.5 to 0.7. To conclude, tension cracks have an adverse impact on the stability of slopes. The location and depth of a tension crack can be estimated using empirical or semi-empirical approaches available in the literature. In this study, a series of numerical analyses were carried out to estimate the stability of unsupported vertical cut in unsaturated glacial till, considering the influence of matrix suction and tension crack. The proposed approach can be used to establish factor of safety map in terms of depth and distance ratio of tension crack, which can also be used to estimate the stability of unsupported vertical cut upon the occurrence of tension crack. One point to be noted is present study was carried out for a one type of soil, which is Indian head till or glacial till, with a groundwater table at 3 meters. Therefore, more extensive study is necessary for various types of soil and levels of groundwater table to justify the findings obtained from this study. Here's a list of references which has been used in this presentation. Thank you so much for your attention.